Preparing for a software engineering at DigitalOcean interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a reliable API for creating and managing cloud droplets? I would expose a versioned REST API with authenticated project-scoped resources. A create request would accept an idempotent key, validate region, image, size, and quotas, then return a provisioning status rather than blocking. A durable job queue would perform infrastructure changes with retrievable steps and persisted state transitions. The API would expose polling or webhooks, enforce rate limits, emit structured logs and metrics, and use authorization checks on every resource access. While answering, focus on resource modeling, authentication, idempotency, validation, asynchronous provisioning, status transitions, retries, rate limiting, observability, and consistent error responses. Question 2. How would you investigate intermittent latency spikes in a production service? I would first quantify the incident using P50, P95, and P99 latency by endpoint, region, and customer segment. Then I would correlate traces with CPU, memory, garbage collection, database weights, network errors, queue depth, and deployment history. I would compare healthy and affected instances, reproduce with representative traffic, and mitigate through rollback, throttling, or capacity changes. Afterward, I would document the root cause, add detection, and create a regression test. Make sure to cover symptom definition, latency percentiles, distributed tracing, dependency metrics, saturation, recent changes, log correlation, controlled reproduction, rollback strategy, and permanent remediation. Question 3. Explain how you would make a distributed operation idempotent. Idempotency means repeated requests produce one logical result. I would require a client-generated operation key, scoped to the authenticated project, and store it with the request hash and resulting resource. A unique database constraint would prevent duplicate execution, while workers would safely resume unfinished operations. Reusing a key with different parameters would fail clearly. Keys could expire after a documented period, but the underlying resource identity should remain recoverable. In your answer, talk about operation identity, client-generated keys, durable request records, duplicate detection, atomic state transitions, retry behavior, expiration, and handling ambiguous failures. Question 4. What happens when a TCP connection is established, and how would you troubleshoot connection failures? TCP establishes a connection through SYN, SYN-ACK, and ACK, then provides ordered, reliable byte delivery. For failures, I would test DNS resolution first, then route reachability, listening ports, firewall rules, security groups, and service health. A refused connection usually means no listener or an active rejection. A timeout suggests filtering or unreachable paths. A reset indicates abrupt termination. I would confirm hypotheses with SS, traceroute, curl, and packet captures. Be sure to mention the three-way handshake, ports, routing, DNS, firewalls, security groups, SYN backlog, timeouts, packet captures, and distinguishing refused, reset, and timed out connections. Question 5. How would you design a rate limiter for a public cloud API? I would use a token bucket keyed by project and endpoint, allowing controlled bursts while enforcing a sustained rate. For multiple API servers, counters would live in a low-latency distributed store with atomic operations and expiration. Responses would include retry guidance and remaining capacity. I would separate limits for expensive operations, protect internal traffic, and monitor rejected requests. If the limiter store failed, I would choose a conservative fail open or fail closed policy based on abuse risk. Focus on the limiting key, token bucket or leaky bucket behavior, distributed state, atomic updates, burst capacity, fairness, response headers, clock issues, and graceful behavior during data store failure. Question 6. How would you safely deploy a schema change to a high-traffic service? I prefer an expand and contract migration. First, I add nullable columns or new tables without changing existing behavior, then deploy code that can read both formats and gradually backfill data in throttled batches. After validating consistency and performance, I switch writes and reads, monitor errors and lock time, and remove the old structure later. Destructive changes wait for a separate release because rolling back application code cannot restore deleted data. Cover backward compatibility, expand and contract migration, online indexes, dual reads or writes, batching, locks, monitoring, rollback limits, and coordination between application and database releases. Question 7. What design choices help a service remain available during a DigitalOcean region or host failure? I would separate failure domains and avoid relying on one host, rack, or region. Stateless API instances could run across multiple zones behind health-aware routing, while data would use synchronous replication where latency permits and asynchronous cross-region replication for disaster recovery. I would define RTO and RPO explicitly, automate backups and restoration, and degrade non-essential features during incidents. Regular failover exercises matter because configuration drift often defeats theoretical redundancy. In your answer, discuss failure domains, replication, stateless services, health checks, traffic routing, quorum decisions, backups, recovery objectives, graceful degradation, and testing disaster scenarios. Question 8. How would you troubleshoot a Kubernetes workload that keeps restarting? I would inspect pod status, restart counts, events, previous container logs, exit codes, and probe failures. An killed status points toward memory limits or leaks. A non-zero exit code requires application investigation. Repeated probe failures may indicate startup timing or dependency problems. I would verify configuration, secrets, image changes, node pressure, and volume mounts. I would reproduce locally or in staging, then fix the root cause rather than simply increasing restart thresholds. Make sure to cover pod events, exit codes, logs, probes, resource limits, kills, configuration, image versions, node health, and distinguishing application failures from orchestration failures. Question 9. How would you build a background job system for provisioning cloud resources? I would persist a job record and enqueue a message transactionally, using an outbox if the database and broker cannot share a transaction. Workers would claim jobs with visibility timeouts, perform idempotent steps, and update durable progress. Transient failures receive bounded exponential backoff. Poison messages move to a dead letter queue for inspection. Per-resource concurrency limits prevent overload, while metrics track queue age, success rate, retries, and time to completion. Discuss durable queues, at least once delivery, idempotent workers, visibility timeouts, retries, dead letter handling, job status, cancellation, concurrency limits, and operational monitoring. Question 10. When would you choose a relational database over a key value store for a new service? I would choose a relational database when the service needs transactions across entities, strong constraints, flexible queries, or reporting. A key value store fits predictable access patterns, very high scale, and simple aggregate ownership, but it shifts joins and integrity into application code. I would model the dominant reads and writes before selecting technology, benchmark realistic workloads, and consider operational maturity. Using both can work, but duplicated state creates consistency and migration costs. Focus on access patterns, transactions, relational integrity, query flexibility, scale characteristics, consistency, operational complexity, indexing, and whether the data model is stable or evolving. Question 11. How do you prevent a cache from becoming a source of stale or incorrect data? I treat the database as the source of truth and use cache aside for many read-heavy workloads. On a miss, the service loads data and caches it with a bounded TTL, writes invalidate or update the relevant key. Versioned keys help prevent old writers from overwriting newer values. I would add request coalescing or locking to prevent stampedes, avoid caching sensitive authorization decisions casually, and document acceptable staleness for every field. Be sure to mention cache ownership, TTLs, invalidation, versioning, write-through or cache-aside patterns, race conditions, stampede protection, negative caching, and consistency expectations. Question 12. Describe a robust approach to handling retries in distributed systems. I retry only errors likely to be transient, such as temporary overload or network interruption, and never blindly retry validation failures. Each request has a deadline, bounded exponential backoff, and jitter so clients do not synchronize. The operation must be idempotent, and retries should respect a shared budget to prevent amplification across service layers. Circuit breakers, meaningful timeout classification, and metrics for retry volume help expose unhealthy dependencies quickly. In your answer, cover transient versus permanent errors, exponential backoff, jitter, attempt limits, idempotency, deadlines, retry budgets, circuit breakers, and avoiding retry amplification. Question 13. How would you secure a multi-tenant cloud service? I would establish tenant identity at authentication time and enforce authorization server-side on every resource lookup and mutation. Database queries would include tenant scope by construction, with separate credentials and policies for sensitive operations. I would encrypt data in transit and at rest, store secrets in a managed system, record security relevant actions, and isolate workloads through network and infrastructure controls. Threat modeling, dependency scanning, fuzzing, and negative authorization tests would be continuous. Discuss tenant identity, authorization boundaries, least privilege, data isolation, secret handling, encryption, audit trails, validation, network segmentation, abuse prevention, and security testing. Question 14. What is your approach to designing observability for a new service? I start with user-facing service-level indicators, availability, latency, correctness, and completion time. I add counters, gauges, and histograms with controlled labels, structured logs containing request and tenant-safe correlation IDs, and distributed traces across dependencies. Dashboards should explain symptoms, while alerts should represent meaningful slow risk rather than every anomaly. I also define retention and redaction rules so observability improves debugging without leaking secrets or creating unmanageable cardinality. Focus on actionable metrics, structured logs, distributed traces, correlation identifiers, service-level objectives, cardinality control, dashboards, alerts, and privacy-conscious diagnostic data. Question 15. How would you diagnose and improve a memory leak in a long-running service? I would confirm steady memory growth using process metrics and determine whether it is heap, native allocation, buffers, or cache growth. Heap profiles taken over time can reveal retained objects, while garbage collection metrics show whether pressure is increasing. I would reproduce the pattern with a controlled workload, inspect ownership and lifecycle assumptions, then fix unbounded maps, listeners, or buffers. Finally, I would add a long-running regression test and alert on slope, not just absolute usage. Mention confirming growth, distinguishing heap from external memory, profiling, allocation patterns, garbage collection, reproduction, workload comparison, remediation, and regression monitoring. Question 16. How would you review a pull request for a production-critical change? I first understand the intended behavior and failure impact, then inspect interfaces, state transitions, concurrency, and error handling. I check authorization, input validation, backward compatibility, resource usage, and whether retries could duplicate side effects. Tests should cover normal, boundary, and failure paths, while production changes need useful metrics and logs. I prefer focused diffs with clear rollout and rollback plans, and I discuss risks directly rather than nitpicking style. Be sure to cover correctness, failure modes, concurrency, security, compatibility, test quality, observability, migration safety, readability, and whether the change is appropriately scoped. Question 17. How would you design a service that remains responsive under sudden traffic spikes? I would identify the bottleneck first, then use stateless horizontal scaling with warm capacity and autoscaling based on saturation and queue age, not CPU alone. Caching and asynchronous work reduce synchronous pressure, while admission control, per tenant quotas, and load shedding protect critical paths. Connection pools and downstream limits must be bounded. During overload, the service should return explicit, retry-aware errors and preserve core operations instead of failing unpredictably. Discuss capacity planning, autoscaling signals, queues, admission control, caching, load shedding, connection pools, graceful degradation, warm capacity, and protecting critical dependencies. Question 18. Explain a safe strategy for rolling out a risky infrastructure change. I would make the change reversible, validate configuration before applying it, and start with a small canary in one failure domain. Automated checks would compare error rate, latency, saturation, and customer impact against a baseline. I would expand gradually only when health gates pass, with a tested rollback that does not depend on the failed component. Clear ownership, incident communication, and post-deployment verification are essential. A change is not complete when the command finishes. In your answer, cover feature flags, canaries, blast radius reduction, pre-flight checks, automated rollback, health metrics, backward compatibility, communication, and post-rollout validation. Question 19. How would you handle an incident where a deployment causes elevated error rates? I would acknowledge the alert, state the customer impact, and assign incident, communications, and investigation roles. If the correlation is strong, I would pause rollout and roll back or disable the feature while preserving logs and deployment metadata. I would monitor recovery rather than assume it. After stabilization, I would build a timeline, identify contributing factors, and create specific actions such as stronger canaries, tests, or alert improvements without assigning blame. Focus on detection, incident roles, impact assessment, rollback or mitigation, evidence preservation, stakeholder communication, root cause analysis, and blameless preventive actions. Question 20. Tell me about a time you improved a system's reliability or developer experience. In one project, deployment failures were frequent because configuration validation happened only after rollout. I added a typed configuration tool, pre-flight checks in C, and a canary stage with automatic rollback. We measured deployment failure rate, recovery time, and engineer interruptions before and after the change. Failures dropped substantially, and releases became more predictable. The key lesson was to move feedback earlier while keeping production safeguards, rather than relying on careful manual review. Make sure to cover the original pain, measurable baseline, technical decisions, collaboration, trade-offs, rollout, results, and what you learned or would improve next. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.